Techniques for materials characterization can be broadly classified into two parts, microscopy and spectroscopy. Microscopy involves observing things that cannot be observed by the naked eye, whereas spectroscopy involves the study of how matter responds to electromagnetic radiation of various energies. We can categorize various techniques with the following illustrative plot. Techniques like SEM, TEM, and AFM offer high spatial resolution but little spectral resolution, whereas techniques like FTIR, UV-Vis, and Raman offer very good spectral resolution but little spatial resolution. However, there are a couple of techniques which can offer the best of both worlds, and one such example is tip enhanced Raman spectroscopy or TERS. TERS is based on Raman spectroscopy, which is highly sensitive to molecular vibrations and depends upon the change in the molecule's polarizability. For instance, the simple symmetric stretching mode of the carbon dioxide molecule affects the shape of its polarizability ellipsoid, which then manifests as a unique signature in its Raman spectrum. Incident light, when scattered by molecules, consists of a major portion whose wavelength remains constant. This phenomenon is known as Rayleigh scattering. However, a small fraction of the scattered light has wavelengths different from its incident value. This phenomenon is known as Raman scattering, which was discovered by the Indian physicist Sir C.V. Raman in 1928. Raman spectroscopy is a fingerprinting technique to identify individual molecules. However, the intensities of Raman scattering are inherently weak, to the tune of 5 orders of magnitude below normal Rayleigh scattering. In addition, like all optical spectroscopies, conventional Raman spectroscopy is hampered by the Abbe's diffraction limit. This formula indicates that it is impossible to achieve a spatial resolution less than approximately half the wavelength of the light that is used to image a sample. The problem of weak Raman intensity can be addressed by means of surface plasmon resonance enhancement. In a nutshell, SPR enhancement involves confining incident electromagnetic radiation onto metal surfaces by means of resonant oscillations of the conduction electrons. Gold, silver, or copper are typically used for this purpose, and SPR can enhance the intensity of electromagnetic fields very close to the metal surface by up to 10 orders of magnitude. To get past the diffraction limit, one can take help of techniques like atomic force microscopy or scanning tunneling microscopy, whose sharp scanning probes can achieve spatial resolutions down to a single nanometer. All this forms the basis of TERS. In essence, TERS involves a scanning probe microscope such as an AFM or STM, whose sharp tip is coated with a thin layer of silver or gold. The tip is capable of precise movements in the X, Y, and Z directions. The sample is illuminated by a visible laser beam using a lens of high numerical aperture so that the spot size is close to 1 micron. As the tip is brought near the sample, the SPR enhances the intensity of the laser on top of the sample, which leads to an increase in the intensity of the scattered light bearing the Raman signature. This scattered light is collected from the reverse optical path and fed to the detector after filtering out the Rayleigh component. There are three possible experimental geometries for tip-enhanced Raman spectroscopy: inverse illumination, side illumination, and top illumination. Inverse illumination requires thin and transparent samples, whereas side illumination and top illumination are good for opaque ones. The advantages of TERS are the high Raman enhancement, high spatial sampling resolution, non-invasiveness, and dye label-free spectroscopy and imaging. No cooling setup is required for this. In addition, this technique potentially enables single molecule detection. When the tip is in the retracted mode, the spectrum of the sample is unremarkable and bears the ordinary far-field Raman activity. But as the tip is brought closer to the sample, the signal intensity increases significantly. As the tip is scanned across the sample, a two-dimensional map of the sample can be constructed whose color code can indicate and identify various molecules, nanostructures, or biological entities on the substrate by their unique Raman signature. The scanning probe equipment can either be an atomic force microscope or a scanning tunneling microscope. AFM setups tend to be more common due to the relative ease of operation and maintenance, but require a laser feedback for monitoring the cantilever motion. STM setups offer higher control and precision but have higher maintenance as well, not to mention the requirement of ultra-high vacuum and electrically conducting samples. TERS has certain drawbacks. The high spatial resolution means sampling of lesser number of molecules, which can play a role in decreasing the total Raman signal intensity. The tip sample distance controls the enhancement, and increasing the enhancement could lead to crashing the tip onto the sample surface. The tip can usually get contaminated with carbon, whose own Raman signal can interfere with the signal from the sample. Scanning probe tips get blunt after overuse, and such tips offer little enhancement, but changing such a tip can result in the loss of an acquired position over the sample and the alignment. In conclusion, tip-enhanced Raman spectroscopy is a challenging and promising technique to enable true high spatial and spectral resolution at the nanoscale, capable of achieving the holy grail of single molecule detection.